In this chapter, we will learn about homolytic cleavage of bonds, which usually results in formation of radicals intermediate. These radical intermediates are important in a lot of reactions, such as halogenation of alkanes. So if you look at this example, methane plus chlorine giving me methyl chloride plus HCl, I would be thinking, oh, it's substituting the hydrogen. Well, in general, that's okay to say, but in reality, it's a radical halogenation of alkanes. Where do the radicals come from? There are two types of bond dissociation. There is the homolytic cleavage, and there is the heterolytic cleavage. Homolytic cleavage is the one that where basically the bond is split into two electrons evenly, giving those electrons back to their atoms. And that's what results in formation of radicals. Where heterolytic cleavage, usually the bond is broken in one direction, where the electrons basically go to the more electronegative atom. And that's what results in having anions or cations. So that's basically the difference between homolytic cleavage and heterolytic cleavage. So in the homolytic cleavage here, you could see that the two electrons shared between the A and B, they are evenly distributed back to the two atoms. And that's what you see here. That's a radical formation of this homolytic cleavage. Same thing applies on the chlorine example. You can see here that we are getting two chlorine radicals. So heterolytic cleavage, where the arrow is different from the other arrow, this arrow more of a fishing hook arrow type, where this one is a complete arrow. You can see clearly the difference between the two. This tells me there's a single electron going in that direction. This tells me there are two electrons going in that direction. So this basically generates a cation and an anion. So we could see here the example of terbutyl chloride, where the C and Cl heterolytically cleaved, and that bond basically goes toward the more electronegative atom, which is chlorine in this case. And that's what you see here, a chloride anion and the carbocation of the terbutyl group. So this reaction, which is a radical halogenation of alkanes, goes through three major steps. And the three major steps are actually listed right here. So the chlorination or bromination, and these are the two common halogenation reactions of alkanes. And we'll see why that is. Why cannot be fluorination or iodination? Now, in this example, which is methane plus Cl2, in presence of heat or light, that pushes the reaction to go faster to get to the product. And every single halogenation of alkanes will always go through these three major steps. And remind ourselves that the outcome will always be an alkyl halide plus hydrogen halide. So if it's bromination, then I would be expecting an alkyl bromide and an HBr side product. So the first major step is the initiation. And when you see the word initiation, you always think of having basically reactants that are non-radicals, giving me products that are completely radicals. And here's an example. So the Cl2 in that halogenation reaction will basically go through homolytic cleavage, and that gives me basically the 2Cl radicals. So initiation, you always form the radical species in the radical reaction. The second step is the propagation. What happens in the propagation? Propagation is basically reacting a radical with non-radical, giving me a product outcome that's going to be radical with non-radical. So that's the difference between initiation and propagation. Initiation, you start with no radicals, you end up with fully radicals, while the propagation, you start with two reactants, one of them is radical and one of them is not, giving me an outcome that will be one of them is a radical and one of them is non-radical. In the propagation step is usually the formation of the outcome of the reaction. So the products that we see in the halogenation of alkanes, which is methyl chloride and HCl, we're going to see them actually getting resulted in the propagation step. So you see here that you have the first step in the propagation, the Cl radical, which came from the initiation step, will abstract a hydrogen. And this hydrogen will be homolytically cleaved from the CH, and that will basically form the HCl. What's going to leave behind? The methyl radical. This methyl radical is needed for the second step in the propagation, which is that radical going to have to react with Cl2. Okay, remember, propagation has to have one radical, one non-radical. So you can't have two radicals reacting together in the propagation step. So the methyl radical react with one of the Cl. Once it homolytically cleaved from that Cl2, you will be forming the major product in the halogenation of alkanes, which is the alkyl halide, plus the Cl radical. And this Cl radical goes back and finds another methane to give you a methyl radical, and the methyl radical goes finds another Cl2, and so on. So the cycle keeps going until it consumes the reactants in this reaction. That's the second step, propagation. The third step is termination. Basically, the end of the reaction will always happen when you have radicals react together to give you non-radicals as outcome. So that's how I know I'm dealing with a termination step. I start with complete radicals, reactant species, to basically end up having non-radical reactions, and that stops the reaction. In the termination step of this reaction, you will see basically that you have two radicals reacting together. You may end up seeing the same outcome as the product of the reaction, but that's not where the major yield comes from. The major yield of the reaction comes from the propagation step. Keep that in mind. Keep that in mind. The other radicals can actually react also in the termination step. So Cl radical reacts with another of the same, methyl radical reacts with another of the same, or as we've seen, Cl radical reacts with a methyl radical to give you basically the outcome. And these are usually side products that are useless to have. The reaction doesn't really depend much on the yield of those steps in the termination step. So once again, the propagation is really a key step in the halogenation of alkanes. In it, you will see the two steps in which you will get basically the two products, the methyl chloride and the HCl side product. So it's important that you always recognize that the yield of the halogenation of alkanes will always actually depend on the propagation step. This reaction is similar in terms of chemistry when it comes to bromination. The difference between a chlorination and bromination is actually the energy. So if I have this reaction, which is again the chlorination of methane, we see here that it has two intermediates. So you're going to have the first intermediate where you're going to be basically giving you this structure, which is the methyl radical, and this methyl radical requires an activation energy much more than the second step, where it gives me the chlorine radical. So you will end up having basically two transition states. One of them is higher than the other, and that's why the rate determining step in the halogenation of alkenes is always going to be the first step that's going to yield the alkyl radical, and that's what's going to determine the reaction rate of the reaction. So that's going to actually lead us to another concept, stability of radicals, which we're going to talk about in a minute. So this slide tells me that the reaction depends on a transition state that's going to require activation energy. What we notice here, if I am doing fluorination versus chlorination versus bromination versus iodination, that the fluorination usually happens at a very, very high rate. It's very fast reaction. Opposite to it will be the iodination. It's so slow reaction. So these two reactions, fluorination and iodination, are not common to be used. One leads to a lot of products that will be useless at the end because of the fast rate of the reaction, and one leads to a very low yield due to the fact that it's very slow reaction. So very common that we see chlorination or bromination of alkanes, but it's not common to see fluorination or iodination. So the conclusion of the halogenation of alkanes, we see that with increasing activation energy, rate decreases, with increasing temperature, rate increases. And that's what we're going to see the difference between bromination and chlorination. Bromination need heat to go forward, while chlorination actually releases heat to go forward. So the chlorination reaction is an exothermic reaction, while the bromination reaction is an endothermic reaction. And what we learned in a previous course, that those reactions that are endothermic, they are usually less favored than the exothermic reactions. Activation energy that is usually negative will lead to a reaction to be spontaneous. Those reactions that lead to entropy value to be higher, these will be more favored than reactions that will have a decrease in their entropy. So we could see here that iodine doesn't react while fluorine reacts explosively. So that's why these two halogenation reactions will be not common to be used. So comparing the two reactions, chlorination and bromination, you could see here that we have the two energy diagrams where one is the bromination and the other one is the chlorination. You could see clearly the difference between the two in terms of energy. One is an endothermic reaction. You could see here that the reactants versus the intermediates require much more energy to get to them, while here the intermediates are actually lower in energy than the chlorination reactants. So we could see clearly that this chlorination reaction is an exothermic reaction. So that tells us right there that the chlorination is much faster to form and to give me the final product compared to the bromination of alkanes. In either of the two, there is a common thing, that is, every single time halogenation of alkanes take place, that halogen will always look for the carbon to carry that radical to be the most stable. So if I look at this reactant, I have a primary, I have a secondary, and I have a primary. What does that primary, secondary mean? Primary, when you have a carbon that's attached to it. So you have a methyl has one carbon attached to it, so that's why these two are primary. CH2 is a secondary because of the fact that it's attached to two. Tertiary, that means that tertiary carbon will be attached to 3 carbons. Quaternary, that's the maximum alkyl substitution. That's when you have 4 carbons attached to it. So in terms of halogenation of alkanes, that most stable carbon to carry the radical will be the one that's going to pick up the halide. So in this case, you could see here the secondary halide is the one that's actually going to be generated from the secondary radical that's faster to form than a primary radical. So this is important to keep in mind. Whether I'm doing bromination or chlorination, is the same scenario. There's a secondary radical will be faster to form than the primary radical. So that's important to keep in mind. So we have basically the ranking of those radicals right here. See clearly that the stability of the free radical determines the reaction rate. The less stable the radical, the more activation energy is needed to get to it. And that's why the reaction will be slower. So methyl radical, for example, will be the least stable in all of these radicals, therefore will be the highest when it comes to activation energy needed to get to it. That's why it would be the slowest reaction to basically have that radical to be halogenated. So every single time you are dealing with a halogenation of alkanes, always think of the stability of the radical. And that stability of the radical will be determining which carbonate is going to be the one that's going to pick up the halogen. So you have the methyl radical will be the least stable, next would be the primary, secondary, and then the tertiary would be most stable among those. However, there are more stable radicals than those. Which ones? The ones that are benzyl or allyl radical. And here's a slide where it shows basically that. So if I have this structure, I have an allyl radical Allyl due to the fact that you have a vinyl group attached to a carbon. This would be called an allyl radical. And here's the reason why this is more stable than a tertiary. The reason is that this double bond can stabilize the radical, and the localization will generate a second resonance form. So having more resonance forms that will stabilize the radical, therefore this radical will be more stable than a tertiary, which is more stable than a secondary, than a primary, than a methyl. And what's more stable than an allyl radical will be the benzylic radical. So instead of having the double bond having a phenyl group, will generate more resonance forms. And that will actually make that benzylic radical the most stable form of radicals possible. Okay. So the outcome, once again, of halogenation of alkanes is always going to be an alkyl halide plus HX, the halide to be basically sitting on the carbon that's going to be the most stable radical in that structure. There is other reactive intermediates besides radicals, which are listed right here. So the carbocation, the carbanion, the carbene. We're going to see one of the chapters being discussed in this course relies a lot on having carbocations. So we will have to basically make sure that we understand how these carbocations are ranked in terms of stability, which is very similar to the carbon radicals. So if you look at this carbocation, which is basically an sp2 hybridized carbon, it has a vacant p orbital. This vacant p orbital can be stabilized through an overlap. What is that supposed to mean? What it means, if I would have tertiary carbocation versus secondary versus primary versus methyl, you will see that the sp3 hybridized carbons that are sitting within those alkyl groups, they're going to actually stabilize that carbocation through the overlap with the vacant p orbital. Same applies to the secondary. Same applies to the primary. No overlap whatsoever with the vacant p orbital on that carbocation when it's a methyl carbocation. That's why it's the least stable compared to the primary, secondary, and tertiary. So the two factors that usually affect stability of carbocations are inductive effect and hyperconjugation. What's inductive effect? Inductive effect having basically alkyl groups that serves as donating effect to the carbocation. So that stabilizes the carbocation. Hyperconjugation is when you have basically an sp3 carbons on the carbon adjacent to the carbocation. The presence of those sp3 bonds will the sp3 orbitals will basically create an overlap with the p vacant orbital, and that secondary overlap will actually stabilize the carbocation. This phenomena is called hyperconjugation. So it's important to keep this in mind. The inductive effect and hyperconjugation is what we use as an argument to justify the stability of tertiary versus secondary versus primary versus the methyl. But if we're dealing with an allyl carbocation, we cannot use the argument of inductive effect or hyperconjugation. What do we use instead? Resonance stabilization. So the allyl carbocation is more stable than a tertiary because of the resonance stabilization. And that's the reason behind the stability of the benzylic carbocation as well. So the benzylic carbocation will be the most stable form of carbocations. Next would be the allylic carbocation. Next would be the tertiary, secondary, primary. Methyl carbocation will be the least stable form of carbocations. So keep in mind, free radicals, stability will be as the following. Benzyl radical, allyl radical, tertiary, secondary, primary, and the methyl radical will be the least stable. Carbanions is another reactive intermediate. The negative charge will be actually destabilized having an electron donating group. So we could see here clearly in this table how the ranking is in the opposite direction of the carbocation. So the carbanions, if it's a methyl carbanion, will be much more nucleophilic, stronger base than a primary, than a secondary, than a tertiary. You could think of it as the steric hindrance factor. the more free the negative charge on that carbon, the easier it's going to basically act as a nucleophile or as a base. So that's the reason behind it. And the carbene, that's another reactive intermediate. We're going to see it in the alkene chapter later on. And that's the story of chapter